In number 11, we have a car initially traveling at 29 meters per second, and it's undergoing a constant negative acceleration of magnitude 1.75 meters per second after its brakes is applied. How many revolutions does each tire make before the tire comes to stop, assuming that the car does not skid and the tires have this radii? Well, we're trying to find revolutions here, so we're dealing with angular motion. The problem is our velocity and our acceleration are given in terms of meters, regular linear velocity and linear acceleration. So the first thing we're going to do on this problem is convert each one of these. So we can convert regular velocity to angular velocity, omega, by taking it divided by the radius, which we know. So in this case, that 29 meters per second up here, divided by the radius of the tire, tells us that the wheels are initially turning at 87.9 radians per second. And we can do the same thing with angular acceleration. Angular acceleration, alpha, is equal to regular acceleration divided by the radius. In this case, the acceleration negative 1.75, they tell us it's negative, divided by the radius of the wheel gives us the angular acceleration of negative 5.3 radians per second squared. And now we can find this. Notice that we don't have the time required for the car to come to stop. Yeah, I know we could find that using the initial velocity and the acceleration, but why not go ahead and use this equation again for part A, the one that does not require time, and just translate it into its rotational equivalent. In this case, we can plug in all of our numbers. We're going to figure out when it comes to a stop. So in this case, the final velocity is going to be 0. The initial velocity is from up above, the 87.9, and we know the angular acceleration, alpha, is negative 5.30. And then we can directly solve for delta theta. Delta theta ends up being this many radians. You're like, oh, okay, great. Well, we got one more step. They actually wanted the answer to A in revolutions. And so how do we go from radians to revolutions? Again, remember that 1 revolution is equal to 2 pi radians. And so you can very quickly just take our number of radians, divide it by 2 pi, and that will give us the number of revolutions. And that's what I've done here. If you take 728 divided by 2 pi, you'll get our final answer, which is this. For part B, what's the angular speed? Well, and that's when it's covered half the distance. I could use a bunch of different equations, but again, I'm trying to keep this simple. Again, we don't have time, so I'm actually going to use this equation a second time. So this is part B, when it's gone through half the total distance. So in this case, we're trying to find this. The initial omega is still the same. The angular acceleration is still the same. But this time I'm searching for omega when the angular displacement is half of the final. And again, whenever we're working in these equations, delta theta has to be in radians, not revolutions. So I'm going back to the 728 divided by 2, half of that total distance. And if you solve this, you'll discover that the angular velocity at that point should be about 63.1 radians per second. Good luck.